Hello students, welcome into our first lesson, and in this lesson we are going to do the following. One, we are going to define the center of gravity of the body. Two, we are going to determine the center of gravity of regular objects. Three, we are also going to determine the center of gravity of irregular objects. And finally, we are going to do some numerical examples involving the center of gravity and moment of force. Let us begin our discussion by looking at the center of gravity. And the center of gravity of a body is a point of application of the resultant force due to Earth's attraction. And it is a point where the whole weight of the body appears to act from. And the resultant force is now the weight of the body. It is also very important to note that a body pivoted at its center of gravity will always balance. For regular or uniform shaped bodies, the center of gravity is at their geometrical centers. For example, a uniform metal rule always balances at 50 centimeter mark when suspended. So one way of determining the center of gravity of objects is by suspension, or you suspend until it balances. Then we have the center of regular shapes can also be determined by construction. Let us look at some of the shapes that we can look at their centers of gravity. And of course, they are regular, meaning that they have a definite shape. And we will start with the square and the rectangles plates. And here we draw the diagonals, or we construct the diagonals at the point of intersection of now the two diagonals will represent the center of gravity of this object here. So it is this point here. So we have the circular plate, and here we construct the diameters, and the point of intersection of the diameters will represent the center of gravity of now this circular plate. So it is this point. And also you need to know that the diameters to be constructed must be at right angle at the point of intersection here. For triangular plates, the perpendicular bisectors of the sides are constructed, and then the point of intersection represent the center of gravity of these objects. And we have, this is our triangular plate, and we will just draw the perpendicular bisector. Maybe you can start with this side here, and the perpendicular bisector will be this one. And also we can move on to the next side, which is this side, and the perpendicular bisector is this one here. Also we go to the third side, which is this one, and the perpendicular bisector is now this line here. And then they all meet at a point, and that point will be now the center of gravity of this plate. Or we have the cylinder, and here we construct the axis, and wherever they will meet, that will give the center of gravity of the cylinder, and that means that the center of gravity is this particular point here. Then we move on to the center of gravity of irregular shapes, and we cannot use the method of construction to determine the center of gravity of irregular shapes. And this is because the weight in these objects is not uniform. Therefore, it does not act at geometrical center. And we will use this method whereby we will determine the center of gravity of irregular shaped lamina, and we need the following apparatus. We need the plumb line, we need a thread, we need a stand, and also we need a cardboard. Then we will proceed as follows. We make 3 holes, that is P, Q, and R, on the edges of the cardboard. Then we suspend the cardboard with the load through hole P as shown below. So this is our P here. You suspend this cardboard. Then you tie a plumb line on the load beside the cardboard. Then after the cardboard and the plumb line have stopped swinging, you draw a vertical line on the cardboard as said by the plumb line. Then you repeat the experiment using the other holes, that is Q and R. Then you draw the lines, and also you need to know where the 3 lines will meet, the point of intersections of the 3 lines, and then try to balance the cardboard with the tip of the pencil at the point of intersection of the 3 lines. Then you note the observation. Then you repeat the experiment with sheets of different irregular shapes. And the observation will be at the point of intersection of the 3 lines, the pencil, when put in that point of intersection, it will balance the cardboard. And therefore, that means that will be the point of center of gravity of the irregular lamina. So that is one of the methods of determining the center of gravity of objects. Let us do some examples. We start with example 1, and these examples will help us to understand the center of gravity and moments of force. Let us go through these examples. The figure below shows a uniform bar of weight W and length 80 centimeters. If a force of 20 Newton keeps it in balance, determine the weight W of the body or the bar. So here we are told that the bar is uniform. As we have seen that for a uniform body, the COG is at the center of that body. So we have this bar, and it is pivoted at this particular point here. So let us go through to the solutions. So we take the moment about the pivot here, and we have the clockwise moment, whereby the clockwise moment is from this line here toward this direction. Of course, the weight will provide the moment on this side because it is at the center here. So you take now the weight W, you multiply by the distance from the point of support to this force here, the line of action of this force, and therefore it is a distance from here to here, which is 10 centimeters. Then you take also the anticlockwise moment, which is from here toward this side, and it will be force, which is these 20 newtons multiplied by the perpendicular distance from the point of support to the line of action of this force here. So it will be 20 newtons times now the distance from here to here. Of course, if the length from here to here is 80 centimeters, it means that the length from here to here is 30. So you have 30 centimeters. Then we say, using the moment force, we have the principle of moment says that clockwise moment is equals anti-clockwise moment. Therefore, it means that 10W, which is this, that is the clockwise moment, is equal to the anti-clockwise moment, which is 20 times 30, which is 600. Therefore, it means that if we divide through by 10, we will get 60 newtons, and that one will be the weight of our bar. Let us also go through another example, example 2. A uniform meter rule of weight 0.9 is suspended horizontally by 2 vertical strings P and Q, placed at 20 centimeters and 30 centimeters from its end, respectively. Calculate the weight, or calculate the force or the tension in each string. So this is now the uniform meter rule, which is suspended by these strings, this one and this one, to produce F1 and F2. And then the weight, as we have seen, it acts at the center, so it will be at the center here. So this is the center of this uniform meter rule. So the solution: the weight of the rule acts through its center, as we have seen, and let F1 and F2 be vertical forces acting on the strings. Since F1 and F2 are unknown, we don't know them, we are not given, taking moments about this particular point, F1 is eliminated. Why? This is because if this one is a point of support, it means that the distance from here to the same point is 0. And now if you take now F1 times 0, it will be 0. That means it will be eliminated. Similarly, taking moments about F2, also F2 will be eliminated. And since the system is in equilibrium, sum of the upward forces is equal to sum of downward forces. So it means that if you add the two forces F1 and F2, you will get this 0.9 newtons. And we can take the moment about this point A here. So you take, we have said that it will be eliminated if you take the moment through here, and therefore it means you take F2 times the distance from here to here, which will be 50, and this one is equivalent to 0.5 meters, which is equal to 0.9. Now the weight you multiply by the distance from here to here, from where the force is, this weight acts here to the point of support, which is 0.3. Therefore, F2 becomes, and divide through by 0.5, divide through by 0.5, you will get 0.54 newtons. But F1 plus F2 is equals 0.9. So it means that F1 will be equal to 0.36. So you take 0.9 minus 0.54 newtons. And that marks the end of our lesson. Hopefully you have gotten the best out of this lesson. And now the work remaining for you is to go through the assignments below. Try to go through these questions, see how far you can go, and the answers are found in our notes also. So it is important you go through the notes once again. You can replay, and then whenever you will not understand, you can also talk to us, Holonet Africa, for more consultation. Until then, let us meet in our second lesson.